So in the last class, I have told you that the there can be many periodic waves, and based on the instantaneous value of the periodic wave, we can calculate the RMS value, average value, and hence the form factor and peak factor can be calculated. Okay. So the good thing about the periodic waves is that we clearly know the limits, so the definite integral can be applied. So let us see this example of triangular waveform. So here I is equal to Im when theta is equal to pi. So as is evident from its peak value, and I is equal to Im theta upon pi. Okay. So this is for 0 to pi value. Okay. So i- if we are taking the RMS value of the current wave for the period 0 to pi, then what happens? We calculate the RMS value I square d theta 0 to pi. We apply the limits and we get IRMS as Im by root 3. Similarly, if we calculate the average value, we can apply the definite integral of 0 to pi and get the value of Im by 2. Okay. So now the form factor is the ratio of the RMS and the average value. So these values can be substituted and form factor and peak factor can be calculated. Okay. So the point is that, as I have mentioned in the previous class as well, that based on the given periodic wave or the wave shape, its geometrical wave shape, we have to calculate the limits and hence apply the definite integral. Okay. So let us suppose that if this triangular wave was to be calculated for pi to 2 pi as well. Okay. Then the function will be different. Okay. Because now from 0 to pi, this equation is of a straight line passing through the origin. So the equation of the line which is passing through the origin is y is equal to mx. Okay. So, but if we have to calculate the function, then we can also use the 2-point formula of mathematics class 11th. Okay. So that we can get the function and then apply the limits. So you all are aware of those formulas. For example, if what is the uh, coordinates of these point, this maximum point, it is pi and Im. Similarly, this 2 pi is given and value is 0. Okay. So 2-point formula is y minus y1 is equal to m x minus x1, where m is the slope and slope is y2 minus y1 upon x2 minus x1. So in this way you can calculate the function and apply the limits. Okay, let's move further. So what is the inductive circuit? It is a coil with or without the iron core and having the negligible resistance. Practically pure inductance can never be had, as the inductive coil has always some resistance, some small resistance. Okay, so pure inductive coil is not possible. Similarly, pure resistive load is also not possible. Whenever we talk of the inductive load, some small resistive load is present, and similarly, whenever we talk of some resistive load, some inductive component is present there. Okay, so what is this choke coil? It is coil of a thick copper wire wound on a iron core, laminated iron core. Okay, so this is the. So now we will check the behavior of R, L, and C components in the AC circuits. First of all, we will calculate the pure resistive, pure inductive, and pure capacitive circuits, and then the mixture. Okay, so you have already studied this in class 12. It is just a revision. So, first of all, we should know what are these resistive loads. So, the resistive loads are the filaments, lamps, heaters, etc. So, what is the circuit diagram? So, this is the circuit diagram in which the resistive load is drawn. So, extra care has to be taken while drawing the resistive load, because in the resistive load it begins with some height and ends with the low. Okay, so one load is there, one source is there, and some current is flowing. Okay, so you have to keep in mind that if you are denoting small letter, okay, or instantaneous current, then you have to use small letter v for instantaneous voltage in this circuit. Okay, so it is connected to AC. So this instantaneous voltage is sinusoidal voltage, or Vm sin omega t. Okay, but if it is equally good enough to represent these values in RMS, or you can say that you can denote that, okay, in the current in the circuit I is flowing, absolutely fine, no problem with that. But then you should denote the source voltage by V, or the RMS value of the V. Okay, so V should be in capital here. So this is the circuit diagram and this is the phasor diagram. Now since I have told you that if two sinusoidal quantities are in phase, okay, then there is no phase difference. So such a phasor diagram is represented on the x-axis with the anti-clockwise direction is shown, and both these components are mentioned with the help of capital letters. Okay, so as shown here, so this is V and this is I. So I is equal to V by R. Okay, so यहाँ, so here you have seen that I is equal to V by R, good enough. So the magnitude of I is shown less. Okay, but if there is no hard and fast, it all depends upon the value of R. So if VR is 1, then V and I will coincide. Okay, but if R is more, then the current phasor will have greater magnitude and voltage will have lesser magnitude. Okay, and if R is more than 1, then current is here and voltage is here. Okay, so it is just a representation, and it is more applicable when we are doing the numericals. When we are just solving this derivation, it's fine always. Okay, so here we are dealing with the pure resistive circuit, and as I have mentioned you that in the pure resistive circuit, the reactive component is very small in comparison to the resistive component. So it is shown like this. So since these are sinusoidal quantity, I is equal to Im sin omega t, V is equal to Vm sin omega t. So now we have to calculate the instantaneous power. Okay. So again, since we are talking of the instantaneous power, it is denoted by small letter p, and it is equal to small v small I. Okay. So these values are substituted, and this is the wave shape of the current scenario. So here the y-axis is having current, voltage and power. Okay, so all these three alternating quantities can be represented in y-axis simultaneously. Okay, so first of all, we can draw this Ym sin omega t. Next is the Im sin omega t. Now, since they are in phase, there is no phase difference between them. So, both these quantities will begin from the same point in the reference axis or the x-axis and terminate at same point. Okay, but their wave shape is same, but their magnitude may be different. Okay, so as I have just mentioned you, it all depends upon the value of the R. If the value of R is more than 1, then current is small. Current wave shape is small. Okay, but if the vice versa, then the voltage waveform will be small and current will be different. Okay, so now the instantaneous value of the power, so vi, so it becomes vm im sine square omega t. Okay, so this instantaneous power is denoted by this. So we can substitute the values to get this. Okay, so Pm is the maximum value of the instantaneous power. It is denoted by Vm. Okay. Okay, now let's derive this. So how we are going to derive this average value and the instantaneous value? So P is equal to Vi, Vm sin omega t, Vm Im sin square omega t, and you are well aware of the trigonometric formulas. That cos 2 theta is equal to 2 cos square theta minus 1 or 1 minus 2 sin square theta. So that formula is used here, and it is substituted here. So this is the um, instantaneous power which we have obtained. So now we are required to calculate the average power. So this is the average power because this is the sinusoidal quantity, and we have seen in the previous class, that in the previous lecture, that the average value of the trigonometric quantities for the full cycle is 0. So it becomes 0, and this becomes Vm Im by 2. So it can be denoted by Vm by root 2 and Im by root 2. And this Vm by root 2 and Im by root 2 becomes these RMS values, and hence these are denoted by capital letters in bold if possible. Okay, if possible you can write in a bold manner as shown, but otherwise at least you should write by the capital letters. So the power consumed in the pure resistive circuit is not constant, it is fluctuating and always positive. Okay, so we can also generalize this formula, but we will do after completion of say inductive circuit and capacitive circuit as well. So now we move towards the pure inductive circuit. So the pure inductive circuit, here the reactive component or the inductive component is very large, and inductive loads examples are fans, induction motor, fluorescent lamp, etc. So this is the circuit diagram shown. So here again the instantaneous current is shown as small letter, and this self inductance is denoted by L, and EL is the EMF produced by this self inductance. So in the pure inductive circuit, the current lags the voltage by 90 degrees. Okay, so the phasor diagram can be drawn and understood in this manner. So first of all, we have drawn the voltage waveform in the reference axis or the x-axis. Okay, now current is lagging 90 degrees. Okay. One more thing we are noticing here, First of all, these are all RMS values, hence denoted by capital letters. This is the RMS value of the EMF developed by the self-inductance of the coil, and it always opposes the applied voltage. Hence, they are in phase opposition, okay, or their phase difference is 180 degrees. This thing is to be kept in mind. So now let us see the waveform. Here again the instantaneous voltage, current and power is shown in the common y-axis. So x-axis is denoted by time. It can be time, it can be theta, or it can be omega t. All are applicable and correct depending upon the situation. Okay. So here we have taken time axis for our convenience. So again, firstly we will draw the voltage waveform, which is the sinusoidal waveform. Now in the phasor diagram also we will derive soon that this current is lagging by 90 degrees. Okay. So current will begin its journey in the x-axis or from the zero reference after the passage of 90 degrees, or you can say pi by 2 radians. So after the passage of 90 degrees, it will follow the sinusoidal wave shape. Okay. So, but we can observe that in the current situation, it is lagging the voltage by 90 degrees. So this is our instantaneous current. So the instantaneous current can be written as Im sine omega t minus pi by 2. Okay. So what is the instantaneous power? Small v into small I. So it becomes v is the Vm sine omega t. Here we have written. Okay. And when we multiply this by Im sine omega t, what happens? Vm sine omega t and Im sine omega t minus pi by 2. So sine of minus theta is minus sine theta. So this instantaneous current can be written as minus Im sine pi by 2 minus omega t. Okay. So sine 90 minus theta is cos theta. So it becomes Im cos omega t. Okay. So now if we multiply this voltage and current, instantaneous voltage and current, so it becomes minus, okay, Vm, Im, okay, okay, this sine omega t and this cos omega t, but the formula of sine 2 theta is 2 sine theta cos theta. So it is replaced by sine 2 omega t by 2. Okay. So this is the how this instantaneous power in the inductive load is represented. So now we can substitute different values of time to get the wave shape of instantaneous power. This. Okay. So one more observation which we can make out from here, that this is sine 2 omega t. Okay. So it means that it is having twice the frequency. So for the same period of 2 pi radians, when current and voltage will complete its one cycle, this instantaneous power will complete its two cycle. Okay, clear? Next thing is that its wave shape is negative to what? To that of the sine wave. Okay, so it is following this negative path first and rising in the second path and completing its cycle in pi radians. Okay, so this waveform is clear now. So now let's move towards its derivation. So when a AC voltage is applied to a purely inductive coil, a self-induced EMF is produced which opposes the applied voltage. And since the coil has no resistance, so at every instant the applied voltage has to overcome this self-induced EMF of the coil. Okay, so this its value is minus LDI by dt. LDI by dt is the magnitude and minus is the sign which denotes that at every point it is opposing. So from the phasor diagram we have seen that V is equal to minus EL. So the voltage which is developed across instantaneous voltage which is developed across this voltage is LDI by dt. Okay, so now we can replace that instantaneous voltage by Vn sine omega t, and so the di becomes Vm sine dt. Now integrating both the sides, sine omega t becomes minus cos omega t plus any constant say a. So experimentally it is found that a is having zero value. So I is equal to minus Vm by omega L. Okay. This sine omega t becomes minus cos omega t divided by this omega. Okay. So from where this L is coming, this di, when it were isolated, this L was going down. Okay. So Vm by L. Okay. So this is the value of Im is equal to minus Vm by omega L cos omega t, and cos theta is sine 90 minus theta. So that formula is used here. Cos theta is replaced by sine pi by 2 minus omega t. And since the minus sign is this, sine of minus theta is minus sine theta. So the final value of the instantaneous current is Vm by omega L sine omega t minus pi by 2. So this omega Vm by omega L is replaced by this Im sine omega t minus pi by 2. So it clearly suggests that instantaneous current is lagging the instantaneous voltage by 90 degrees at every point. Okay. So again, we are not concerned with the magnitude or amplitude of the waveform. Okay. It will be lagging, that is good, but magnitude of the current may be greater than the voltage or vice versa is also possible. Okay. So since this is given as Vm by omega L, Im is given by Vm by omega L, and we know the Ohm's law is equal to IR, which is applicable for AC circuits as well. So this is the inductive reactance of the inductive circuit, and also it is denoted by XL. Okay, inductive reactance. So inductive power we have just uh, now we will calculate the instantaneous power, which we have calculated in the waveform as well. So this is the VI P is equal to VI. So Vm sine omega t, Im sine omega t minus pi by 2. Okay. So the power measured by wattmeter is the average value of the P, which is 0, since the average value of the sinusoidal quantity is 0 for the complete cycle. Okay. So if we are talking of the average value for the complete cycle, it is 0. Okay. So what is happening in the different quarters? So in the second quarter of the cycle, the current and the magnetic flux of the coil increases. Okay. So what was happening? The suppose this is the our voltage wave. So current was starting after the 90 degrees. Okay. So that is what it is telling, that during the second quarter, so this is this first quarter. So this is, you can say, the second quarter. So during the second quarter, what is happening? The current and the magnetic flux of the coil increases. It is increasing. Okay. Current is increasing as shown, and in previous class you have studied that flux is directly proportional to current in the self inductance. So we can say that its magnetic flux is also increasing, and it is drawing the power from the supply source to build the magnetic field. Okay. So the energy which is stored is half Li square. And now what happens in the next quarter? In the next quarter, the current is decreasing. Okay. Here we can say now the current is decreasing. But since I have told you that the coil is having the property that it opposes the source, okay? So, or it try to negate the change, okay? So, earlier it was opposing for the current built up, it was not allowing out, it was resisting the current to rise. But if the current is reached to its maximum or level, then it resists to decrease. So you can say that it always provide the opposition. Earlier it was opposing to raise the current. Now it is opposing to decrease the current. Okay. So when it is doing some opposition, some energy is to be consumed. So the energy which is gained in the second quarter, half Li square, is used to stop current from decreasing. Okay. So that is used. So now it is acting as a generator of electrical energy because it is using this electrical energy to stop the fallout of the current. Okay, but it does not succeed and current reaches its zero value. Okay,